5.2 area under the curves, approximating area under curves, part 3. We're going to use Riemann sums. This is a sigma notation. In this middle here, this big black Greek letter E is called sigma. And Riemann used this to represent summation. So we call this summation notation. And what we have here is at the bottom we have what we call the index, and it could be k. And notice the function here, this part, the function is k. Those can change. We can be n, it could be p, it could be q, whatever letters we want for the index, it doesn't matter. But the important thing is under the sigma, we have the lower limit, or for what values we want to start, usually 1, and how many approximations, or basically how many intervals do we want to use over subintervals over our entire interval. So we have this lower limit here, k equals 1, below the sigma, and above we have the upper limit, which is telling us how many truly we want to do. So then we use this notation for area. Here, area is equal to the summation of the heights. Remember, this is to represent heights. And this is going to be representing the delta x as our widths of our rectangles as we go ahead and try to sum up the areas under a curve. So we're going to use these notations, and we're going to have some shortcuts here that just kind of need to remember sums of positive integers. So we have a constant, which is easy because then it's just a horizontal line, and we basically are just doing length times width, or width times the height. In this case would be the n. So I'm sorry, the n is the width and the c is the height. And then we have, just for k, we can use those summation shortcuts for sequences. And then we have k squared and k cubed. You would just plug in what you needed to for your formula for those. So then I'm going to go ahead and I'm going to move on to left, right, and midpoint Riemann sums in sigma notation. So we have here that we can use the 3 different cases. Remember, these are going to be on an intervals from A to B. And we have the 3 cases. We're going to use this area here. And if we wanted to find left, we're going to use this as our x sub k values in our function for left. And then we have the one that's the right, Riemann sum for our x sub k values, and our mid point for the Riemann sums. So we would just try to figure these out first and then go from there. So for example 43, the function is the square root of x on the interval from 0 to 4, and we want to use a large number of subintervals. So this is n equals 40. So remember, the more subintervals we do, a better approximation with the rectangles we get. So we find out delta x first, and that's what I have here. It's 4 minus 0 over our subintervals of 40, and I get 0.1 or 1/10, whichever notation you want to use. For our left approximation, remember A is the end point we want to start at, so it's 0. And we see that we have k minus 1, which is part of that formula. It would be delta times delta x, which we said was 1/10. So I just rewrote it here in this last row here as that. You can also use 0.1 k minus 0.1, which is probably what I'm going to do. It's easier to put in the calculator. If I want to go ahead and calculate this in the calculator, I'm technically using this summation. Oops, sorry, I put the point in the wrong spot. 0.1 k minus 0.1. Oh, knew I'd get it there. And then we want to times the delta x, which we said is the delta x is 1/10 also. We just said it. So remember, this is our height, and we got to times the width. But we had that kind of constant rule that we could factor out. So if it makes most sense, instead of putting it in there in our summation, I'm going to put it here outside. You can write it as 0.1 also, or 1/10. I wanted to make sure we can make sure that we got a height going and the width going of our rectangles. So if you want to go ahead and evaluate this in your calculator, two ways to do it. You can do the left, right, and mid rectangular approximation method that we have programmed into our calculator. You would get the correct answers. Or if you do not have the program in your calculator, you can remember that we can use, this is how it should look. I'm sorry, starting with summation of the sequences, you're going to want to put your function in, what variable it's in regard to, and where you want to start and then where you want to stop. So the steps to finding this on the calculator, last step after this would be multiplying it by 1/10. We have to make sure because I factored that out. So if I want to do this, I'm going to hit second, stat, and I'm going to arrow twice over, and then I'm going to see number 5 is the summation. So I'm going to press that 5, and I'll have, all of a sudden, I'll have that sum up. So then when you want to go and get the rest of this, we're going to go ahead and do second, stat. We're going to arrow over to the right once, and it's going to be number 5 again. We can press, and all of a sudden we'll have, oops, did that again, sequence. And it'll come up like this. And then we want to go ahead and we can type in our actual function at this point. So I'll put a comma there, but you really want to go ahead and just do the square root, depending on your calculator. I'm going to put 0.1 x, because instead of k, minus 0.1, and I'll make sure I close that parentheses. So there's my function, and then I'm going to do comma, my variable would be x. I'm going to start at 1 and I'm going to end at 40. I'm going to close twice the two parentheses. I have two open. I need to close it twice. So I have the correct number of parentheses. You hit enter and you should get an approximation. For number 43, the left approximation is 5.227 for the area. So you would do the same process for then using what we had for the little shortcuts for the x sub k's, and we would do the right and midpoint approximations. So there's two ways to do it. Your program that we have already programmed in the calculator, or using what is already programmed into the calculator for us. The last thing I want to talk about, and this is going to be if we were given, just refresh our memories, something that said an increasing function. We know that's increasing from left to right. So I'll put here increasing. Then if it's an increasing function but has a concave up, what would that look like? So I think it would be best to show that as, let's see, increasing but concave up. All right, and then we want to have increasing but a concave down. We would have that. Number 69 is asking if we were given this and using either right, left, or midpoint approximation, they want to know, is it going to be overestimating or underestimating? So let's assume right now we want to talk about left. So we're going to use left approximation. So remember, if this is a straight one, we have, we're only the left corner of our upper width is hitting the function. So definitely that one would be increasing, but it looks to be underestimating. So same thing if it's concave up, left approximation. Looks like to be an underestimating. Even with our concave down but increasing function, left is still underestimating. So if I wanted to go ahead and say, well, what about if we had these same things, increasing but concave up and concave down, but we want to use right approximation. So we'll have right here. And we would see here if right would look like this. And this, every single one of them looks like it would be overestimating. Same with concave down, but in the increasing function. So if we wanted to, we can also talk about, well, what about its decreasing function? So from here, if I have a decreasing function, but concave up, it looks like I would look like that. I would have a decreasing function, but a concave down, I would look like that. And then we can do, you just would draw quick pictures or try to picture in your mind left and right approximation for our rectangles, and would it be over or underestimating them?